Hello, this is pure bending example number 4. This problem reads that a beam section shown below on the left is a W18 by 106. Given that the beam is made out of steel with a yield stress of 36 KSI, calculate the moment M sub Z that will cause yielding in the cross section. So this is a problem that would be typical for a structural engineer or a civil engineer doing a problem with a steel cross section. We need to know how much moment is allowed on the section before the section reaches its yield strength. So one thing I want to point out about this, however, is that it's this section on the left that is the beam that is being considered. This section over here that's shown on the right is the section that corresponds to the tabulated properties in the back of the textbook. So the reason that I need to point that out or want to point that out to you is that the axes are different. So in the section over here on the left, we have a y-axis vertical, but the horizontal axis in the cross-section of the beam is the z-axis, whereas over here on the right, the horizontal axis in the section of the beam is the x-axis. So that can be confusing when you're just getting used to working with these sections, and I just wanted to point that out to you. So the image over here on the left is the image that goes along with the problem definition. So the moment that's applied to the section is the moment about the z-axis, m sub z, whereas the section over here on the right is the cross-section definition that goes along with the definition of the properties in the back of the textbook, the tabulated properties. Okay, so here we are in OneNote, and I don't have the problem definition, but of course I do have the image of the problem. So one of the first things that I'll do is I'll refer to our equation sheet and look at the bending equations that we have to identify which one we can start with. And we'll start with the equations that we've been using for this segment, and that is going to be that sigma is equal to minus m times y divided by I. And in the context of this problem, where we have the z-axis as the axis there, then this is m sub z, this is I sub z, and this is going to be a stress in the x direction. All right, so with that in mind, what we want to do is figure out what the maximum stress is. So we want to figure out what the maximum stress is. It's going to be the maximum stress in the x direction. So we're going to set that equal to an m sub z, and in order to find the maximum stress in the cross section, we're going to be looking at the fibers in the cross section that are furthest away from the neutral axis. So that means that we're going to be looking at y max or y min, and then we divide by I sub z again. So I should have crossed these up here. Too late now. All right, and then a lot of times in your textbook, you'll see that that's equal to, well, let's just do away with the negative sign. We'll say that's an m sub z times c max and divided by I sub z. Or you could write that, excuse me, sigma min is equal to m sub z times c min, and that's equal to, or divided by I sub z. So then over here, this would be y max, and that would be equal to c max. This would be y min equal to c min. Excuse me. Sorry. All right, so we can calculate the stress at any location in the cross section y. When we look at the stress in the maximum fiber, the extreme fiber rather, the fiber that's furthest away from the neutral axis, we often call that location y equal to c. In this case, the C would be the same for the top and the bottom because it's a doubly symmetric cross-section. It would be positive in one case and negative in the other case, strictly speaking. In some cases, though, if you have a cross-section that's only singly symmetric, maybe something like a T-section like that, where you have a neutral axis up here, then you would have one value of C for the top and a second value of C for the bottom. I didn't draw that very good, but so you would have two values of C in that case. That's not within the scope of this conversation, however, so I'll just go ahead and erase that. Whoops. There we go. All right. Now, so the next thing that we need is to know what the moment of inertia is. So I'll go to our table here for that moment of inertia. And this is basically the same table that we had on the first page. So a couple of things to know. We're looking at a W 18 by 106. So for the W 18 by 106, the way that this works is the W stands for W section or wide flange section. The value of 106 here indicates that the section has a weight equal to 106 pounds per foot. So each foot of that cross section weighs 106 pounds. And this number here is the nominal depth of the section. And the depth of the section is here, D. That is equal to 18 inches. Now, why do I say nominal depth? Well, it's because nominal means that it's approximate. If you look at this range of W18s here, you can see that the depth ranges from 17.7 all the way up to 18.7. So in the case of a W shape, that depth is really just the nominal or the approximate value. Okay, now for us, what we're interested in is the section properties for the W18 by 106. Specifically, we're interested in the moment of inertia, so we take back that I is going to be equal to 1910 inches to the fourth. Now, in this table, it's tabulated as I sub x, but that's the horizontal axis through the section of the beam. So when we go back over to our work here in OneNote, we know that I sub x in the table is equal to I sub z here. So I'm going to write this down. I'm going to work in the context of sigma max. So sigma max is equal to m sub z times c max divided by I. So let me go ahead and write in I before I forget what that number is. It's 1910 inches to the fourth. Now Cmax, we need the depth D. So we go back over here and the depth of that section is 18.2. So if the overall depth of this cross section is 18.2 inches, then this is going to be 18.7. I said 18.2, I meant 18.7 divided by 2. So like that. And if we want to make sure that yielding is not going to occur in this section, then we set that equal to the yield stress for the cross section. And I think that in the problem statement, it was stated that the yield stress was equal to 36 KSI. So what we can do now is then solve for m sub z, and that'll be the moment that'll cause yielding. So we could say that m sub z is equal to 1910 inches to the fourth times 36 KSI divided by C, which is 18.7 inches divided by 2. And what we get out of that is a moment m sub z that causes yielding that's equal to 7,342 kip inches, or if we convert that to kip feet, then we divide by 12 inches per foot and we get 611.9 kip feet. So that's the yield moment, the moment that causes yielding in the cross section. Now, as an aside, we have a letter that we use to indicate the ratio of I over C. And so we often use I over C in our calculations, and we use the letter S for that. And this is the elastic section modulus. So I is in units of inches to the fourth or millimeters to the fourth. C is in units of inches. So S is in units of inches cubed. So in a lot of cases then we would say that sigma is equal to m divided by s. I've dropped the minus sign there. Or if we're looking for the yield moment, then we can go in and say that the yield moment m sub yield or m sub y is equal to sigma sub y times s, or a lot of times we would write that as f sub y times s. And that would be the form that we would commonly use in the design of a steel cross section. All right. Hope this helps.